Okay, so again, we're going to be talking about forces. Forces are a push or a pull. So when you push a door open, you're applying force to change the direction of the door. When you pull a door open, you are using force to open the door in a specific direction. Okay? So the definition is a push or a pull exerted on an object. Forces affect motion in several ways. Forces are how we initiate movement, how we get something to move. If you need to move a desk or you want to rearrange your room, you have to apply force to the furniture to get it to move to where you need it to be. If you want to move faster, you'll apply force. If you want something to move slower, you'll decrease the amount of force. If you want something to stop moving, you have to apply a force. So when you're bowling and you throw a bowling ball down the lane, that bowling ball is going to keep rolling until another force stops it, which is going to be when it collides with the pins or the sidebars. Okay, when it makes that collision, the force is changed and the ball slows and stops moving. But without that collision, without that other force, the bowling ball will continue to move. Forces also cause things to change direction, and they cause things to change shape. Think about when you crush a can. Does the can just crush on its own, or do you have to apply a force to it? So we measure forces in newtons with a capital N. This is a really important unit. So please remember, newtons is a capital N, and we use a spring scale. Forces usually act in pairs, which means there is a force that's initiating the direction, and there's usually an opposing force. So as we're walking, we're applying a force that's moving us forward, but gravity is a force that is pulling us down. Does that make sense? Forces also act in a particular direction. For example, I mentioned gravity pulling us down. Friction is usually an opposing force, meaning that its direction is going to be opposite of the other force. So when we talk about gravity, gravity is always present unless you're in space, and even then it's present. But gravity is always going to be a factor here on Earth. It's the force of attraction between all objects. Mass and distance have an effect on gravity. So for example, me as a person, my mass keeps me on the ground. In fact, gravity usually pulls me faster. If you drop a bowling ball and a feather, the bowling ball should hit the ground faster because it has more mass. And then think about how light helium is and how light air is, and how gravity does not affect it as much as it affects a baseball or another more solid object than air or helium or some type of gas. You guys may have noticed from your vocabulary homework that I talked about friction. Friction, again, is a force that opposes motion between two surfaces that are touching. So back to my bowling ball example, the bowling lanes at the bowling alley have little to no friction because they want the bowling ball to accelerate as quickly as possible down the lane to build up more force when they hit the pins, because that's how you knock the pins down. So you'll hear me describe bowling as an example for forces. All of Newton's laws can apply. Friction will cause an object to slow and eventually stop. So on a soccer field, when you kick the soccer ball will eventually stop due to the friction of the grass that is opposing the forward force of the ball. So when we kick a soccer ball, it's going to continue moving forward until the grass slows it down. some surfaces have more friction than others, like sandpaper, different things like that. I'm trying to think. Think about carpet versus hardwood or wood floors. Floors with carpet or floors without carpet. When you're running around in your socks, do you slide around more on the wood floors or do you slide around more on the carpet? Right, you slide around more on the wood floor because there's less friction. When you're in your socks and you're in the carpet and you're sliding around, the carpet and the socks have a lot of friction, so you won't move as fast. But on the wood floor, you can slide and skate all over the place. That's another reason why like skating rinks are kept smooth, because if you've ever been ice skating and the ice rink wasn't smooth, friction causes you to fall or trip. Whereas if it's smooth, it's much easier just to glide right across the ice rink. So force and direction. More than one force can act on an object at a time. So let's think about this. Again, when we're walking, we're applying a force in one direction, but gravity is pulling us down. So that's an example of more than one force working on an object at a time, but in different directions. The force that I'm pushing forward is greater than that of gravity. That's why I'm able to change my movement. So let's just kind of keep that in mind. How much force is needed to move things, and if all the forces on an object are equal, what will happen? So a force can push or pull in any direction, but what happens to the object when the forces act depends on two things: how strong the forces are and what's the direction of the forces. So if all of the forces are in the same direction, you're most likely going to have movement in that same direction. But if the forces are all in different directions, then we have to consider, are the forces equal? Where is the stronger force? And that'll help you determine what direction the object will move. So when you press a light switch to turn the light off, you push down. You apply a downward force, and the force that you're using is greater, so the movement is down. But what about when you launch a rocket? Think about the force of gravity pulling that large rocket down to the ground, and then the force of this explosion right here, how much greater that has to be to push the rocket up. Okay, so we have multiple forces acting here, but the force coming from the explosion and the smoke is greater than that of gravity, so the rocket is moving up. When you push the basket, the more stuff you add to your basket, the heavier the basket gets, the harder it is to push. But again, you are pushing your basket forward with more force. So that's why the basket moves in a forward motion. This is a good example for friction, because if you have something on your wheels, on the wheels of the basket, or the wheels are weird, the basket's harder to push, correct? Which means the force, the opposing force, is as strong, if not greater, than the forward force that you use to push the basket. Okay, and these are just notes. I'm just trying to get your mind thinking about why things move. How does movement work when you have all of these different forces working on objects, including ourselves? Okay, kicking a ball, that ball is not going to move until a force is applied to it. So the soccer player kicking the ball is applying a force. And because the force from his kick is greater than that of gravity, the ball is going to move in the same direction that he kicked. Okay? When you hammer in a nail, the force coming from your motion is greater, so the nail is going to move in the same direction, which is down. Are there any questions about these examples, or do you have some examples of your own that you would like to share? So net force. Net force is the overall or total force. It is the total force on an object when all the individual forces acting on the object are added together. So we calculate net force by adding up all of the forces on an object. When we calculate net force, when two or more forces are combined. To find net force, when they're in opposite directions. So we have an arrow pointing up to indicate an upward force, and we have an arrow pointing down to indicate a downward force. We will subtract. Okay? So when you have arrows in opposite directions, you will subtract. Now there are no negative forces, so the bigger number will always be on top. Okay? Bigger number will always be on top. And that's how you find the net force when they are in opposite directions. But when we are looking for the force, net force, when all the forces are in the same direction, so for example, I need to move a big dresser, me and Cody are on the same side of the dresser, pushing the dresser in the same direction, we're both applying a force in the same direction. And so what we would do is we would add my force and Cody's force to find the total force, the net force that's acting on that dresser. So when your arrows are pointing in the same direction, you are going to just add them together. Okay? So let's practice some examples. What is the net force? Your first step is to identify the directions of your force. So this force is being applied to the right, and this force is being applied to the right. So that means I need to add 10 newtons plus 10 newtons. The net force on this box is 20 newtons. And what direction is this box going to move? It's going to move to the right, the same direction that the force is being applied. Okay? So let's do the second example. First step is to identify the direction of each force. The first one is being applied to the right, and the second force is being applied to the left. So these, even though both of these arrows are both pointing at the box, they are pointing in different directions. These are opposing forces. So that means we need to subtract 10 newtons minus 10 newtons. The net force is 0. So what direction is this box going to move in? Good, really good. So when we have a net force of 0, we're essentially, all our forces are equal, 10 and 10, for example, and in the same direction, when all of the forces are equal and in opposite directions, 10 and 10, the net force is essentially 0. They all canceled each other out. So this box is not going to move. So when you have a balanced force, a net force of 0, there is no movement. Movement can only be caused by unbalanced forces. So the first example has a net force of 20 newtons. It is not balanced. All of the force is being applied one way. So the box is going to move in that direction. So let's do a couple more examples. What is the net force on this box? First step, identify the directions. We have 10 newtons to the left, and we have 10 newtons to the right and 10 newtons to the right. Because both of these arrows are pointing the same direction, I'm going to add them together. So we have 20 newtons to the right, and we have 10 newtons to the left. So they're going in opposite directions. We need to subtract 20 newtons minus 10 newtons. This box has a net force of 10 newtons. What direction is the box going to move in? This box will move to the right because there is a greater force on the right side pulling the box to the right. Okay? The right side has more force. Okay, so let's do another example. Here we have a book. Force 1 is applying 20 newtons to the left, Force 2 is applying 18 newtons to the right. Are these going in the same direction or opposite directions? They are going in opposite directions. This one's going to the right and this one's going to the left. I find it helpful to write that. Pointing to the left and this one is pointing to the right. So when they're in opposite directions, you need to subtract. So 20 minus 18, our net force is 2 newtons. Okay, what is the direction the book will move? Where is the greater force being applied? Good. The book is going to move this way because there is a greater force being applied. So, balanced forces. Equal forces acting on an object in opposite directions. So when it is equal and opposite, it'll be balanced. Balanced forces do not change motion. They do not cause changes in motion. They will be equal and opposite, and the net force will equal 0. Unbalanced forces are any number but 0, and they will always cause a change in motion. The net force is greater than 0. The force is unbalanced. Okay?